Hey there, you sweet potatoes. I'm Teacher Jess, and welcome back to Geo Cafe. Hope you're doing well. So I thought I'd do another video for my matrics. And they seem to be struggling with the atmospheric science, so I thought I'd do one on anticyclones for them. So hopefully this helps. Like I say, if there's anyone who's busy facing exams or maybe needing help with anything, you can leave a comment. I can always go back to that and put together a video, maybe answering specific questions. Yeah, but let me know. Okay, not working. So let's first go with the difference between cyclonic and anticyclonic. Cyclone or cyclonic in the southern hemisphere looks at a clockwise direction of air. In the northern hemisphere, it looks at an anti-clockwise movement of air. Okay. Another important thing to know is that where you have a cyclone, you would have rising air. So your air would be converging at the ground and it would be rising up. Because it's rising, I'm lifting the weight off of the ground. So I'm relieving the pressure and you have less pressure on the ground. So where you have a cyclone, you have rising air, you have low pressure, you have converging air, and because the air rises, it will cool and form clouds. So cyclones are also associated with clouds. Then anticyclones are the opposite in every way. Anticyclones in the northern hemisphere move anti-clockwise. Oh, sorry, in the southern hemisphere move anti-clockwise, and in the northern hemisphere move clockwise. So an anticyclone, we have air that is sinking. It is sinking air, it is diverging when it gets to the bottom, and because it's pushing on the ground, it's placing pressure on the ground. So you have a high pressure system over here, and you have air diverging, so pushing apart. Another thing you'll notice with the lovely sun over here is that you've got clear skies, no clouds. I thought we could just quickly look at photos. If I look at a cyclone, so here you can see all of the clouds around it, and in the middle it's clear. Where it's clear, that is where the air is sinking, pushing down. It has a high pressure system, and for clouds to form, you need the air to rise. I thought we'd also take a look at null school. Okay, so I don't know if you remember null school from one of my earlier videos. This shows you how the air is moving throughout the globe. And I want us to take a look at the air here in the southern hemisphere. It's moving in an anti-clockwise direction, which means it's an anticyclone. And right in the middle over there, I would expect that to be clear, so no clouds. I'm going to change the view to, yeah, this is like the cloud overlay. There you can see that. There you can see that there's clouds all around, but not really anything in them. But if we look in the other direction, go back to the wind. Find something that's clockwise. Yeah, smaller. There we go. That's moving clockwise. So that's a cyclone. So over here, you would have a low pressure system. You would have air rising. You would have condensation, and you would have clouds, maybe rain. So let's put the cloud cover back on. There you go. There you can see the little line of clouds. And you might even recognize that this is a mid-latitude cyclone. Then the other thing that I wanted to show you is called the tricellular model. So it's a model that explains the circulation of the air throughout the whole atmosphere. Yeah, that looks okay. Main reason why I wanted to pull this up is I want you to take a look at which way the air moves vertically. So here we have rising air. Rising air, air is lifting off of the ground. I'm relieving the pressure, so it's a low pressure system. Rising air, that also tells me that this is a cyclonic area. Low pressure systems, cyclones. Okay, over here by the more or less the 30-degree line, 30-degree latitude line, we have air that is sinking. The sinking air presses down on the ground. It creates a high pressure system, which means no rain. Oh, that's perfect. Great. So we were talking about how over the equator we had the air rising. There, you have the air rising. That means that this is a low pressure system. And you'll have condensation, you'll have rain. That's what we're seeing over here. So here we have the hot air, it's rising, low pressure system, rain. Happy. So north, we have the air sinking over here. That means high pressure system. It means anticyclone, less rain, or no rain sometimes. And that's where we have the state. So what's happening over here, the air is sinking down and you need air to rise for it to condense. So all along over here, we have what we call a belt of anticyclones. It's not quite as clear as what I was looking for, but here you can see the H for the high pressure cells. And you can see that there's two on either side of South Africa. So I'm going to take a bit more time to look at those and what those do and how they impact South Africa. Okay. Another important thing to know about cyclones and anticyclones is that they are very much related to temperature. So where you have warm air, you would have air rising. If air rises, it's lifting weight off of the ground, so you have a low pressure system. Where the air is cold, the air will be dense and it will sink. It will push down against the ground. So you have a high pressure system. Where you have warm air or hot conditions, you will have air rising. Where you have cold air, you have air sinking. Okay, I hope that makes sense. So let's just to recap that one more time. So we've got the subtropical high pressure, where you have air that is sinking. You can see it's coming down over there. It is diverging at the ground, so the wind is blowing away from it, and it is spiraling. Is that clockwise? Looks clockwise. I think this image is from the northern hemisphere. Yeah, well, in the southern hemisphere, it would be spiraling anti-clockwise. Okay, so these are the two anticyclones that influence South Africa the most. So we have one over here to the east, that is the South Indian anticyclone, the high pressure, and one to the west, the South Atlantic anticyclone. Okay, South Indian, South Atlantic. We also have one that we refer to as the Kalahari anticyclone. The Kalahari anticyclone isn't like the other cyclones along that section. It's more season dependent. So it's related to if it's summer or winter. It doesn't disappear, but we don't always see it on the map all year round. So this is a normal map, or a, call it an average synoptic weather map of where we would find these anticyclones. So the South Indian one over here, you can see it's spiraling outwards, it is diverging, the wind is blowing away from it. It's blowing in a anti-clockwise direction. You can see it spiraling that. Here, same thing, South Atlantic anticyclone. You can see it spiraling outwards like that. Okay, but in winter, we see them shift. All of these systems shift slightly north. So they'll all move up north, and that includes these high pressure cells over here. So during winter, the high pressure will move towards the north. These ones over here. And in summer, they will shift a little bit more down towards the south. That's one of the ways that you can notice these seasons on a synoptic weather map. In winter, it will be further north, further towards the coastline. In summer, it will be further down and actually have shifted away from the coastline. It gets further south. Okay, what this means for weather in South Africa. So for starters, most of South Africa, and I say most because Western Cape is an exception, but most of South Africa will have clear, rainless winters. So they would have clear skies, sunny weather, and because the air is sinking with the anticyclone, they won't have any rain. A large temperature range, that's, well, one, because it's quite far inland, the temperature fluctuates a lot, and two, because there's no clouds that kind of act as an insulating barrier. Very cold air immediately above the plateau. So if we have ground level, you will have cold air directly above that ground level. That cold air actually creates something of an inversion layer. Let me see if I can find a picture of the layer. Oh, here we go. So we have the cold air because the ground is cold, and you have cold air above, or you have the subsiding air from the anticyclone. You see over here, you have this air sinking, you have the cold air over here. You get what is called a temperature inversion. So it's a layer of warm air. So cold, then warm, then cold again. I won't go too much into how the temperature inversion forms. It's a result of the pressure that's being applied to the air. So when air is under a lot of pressure, it can be warmed, especially if it's dry. So dry air that sinks and pushes against the ground, or as it sinks, it warms up. That's why we have this little section of warm air in between. That section of warm air will also block any rain from coming in, right here. So if we have moisture from the ocean and it tries to blow into the coastline or inland from the coastline, it will have to blow up the mountains, up towards the plateau. Towards the coastline over here, it's green, so that's marking the low altitude areas. And then the red and orange is supposed to show the high altitude areas. So you can kind of see that most of South Africa's interior is quite high in altitude, which means that it's all a plateau. And if wind carrying moisture is trying to blow inland, it has to climb up this plateau. But where we have this temperature inversion, the air can't rise. So the rising air can't get through that temperature inversion. So it's blocking its path up the plateau. And we sometimes see this. We don't actually realize that we're seeing this on a day-to-day basis. Where's that photo? Yeah. This is what a temperature inversion looks like. You can see this is, I think this is smoke, or could maybe be a bit of mist, but this quite clearly smoke. Here you can see the smoke is all getting trapped and it looks like it's being caught under this layer. That layer is the warm air. So this is cold over here, this is warm over here, and it can't rise through it. That is why you get this, you usually see this early in the mornings, maybe like in winter time. You'll see this very early in the morning before the ground starts to warm up. This is what happens with the moisture that's trying to get inland into South Africa. It can't rise up the plateau and it can't get through the inversion layer. So it can't get over this little barrier over here. And then it can't bring any of the moisture into South Africa. Yeah, I hope this is making sense so far. Okay, let's see, are we missing anything? We have the dry air sinking, we have an inversion layer, we have moist air from the Indian Ocean is blocked by the inversion layer. Okay. And it is important to note why we want the moist air from the Indian Ocean and not the Atlantic. So I'm always pointing out over here, this air blowing in. But from the other side, over here, this is a cold ocean current. Cold ocean currents means that there's not much evaporation happening. You need a warm ocean current for significant humidity. That humidity then comes inland and brings the rain. Over here, the cold ocean currents, they can come in, the moisture can come in, but there's not much moisture to begin with. Yes. So this is what I was referring to. You have all of this greenery over here on the east side because that's where we have the warm currents. So that brings in moisture, it evaporates a lot of the water, so you have high humidity and you have high rainfall. On this side, it's dry because we have the cold ocean current, not much evaporation, not much rain. Hopefully, anticyclones in winter are starting to make sense. I will also point out that the Kalahari anticyclone is most prominent in winter. The reason why is because the land is cold. So if the land is cold, it means that the air above it is also cold and it's dense. When the air is dense, it sinks. When it sinks, it presses onto the ground, it applies pressure. That is why we have this high pressure system over here. That's why we have the Kalahari anticyclone. Oh, that's why it's visible. So when I'm doing synoptic weather maps with my students, I always point out certain key things. How you can tell which season it is. The one is look for a mid-latitude cyclone. If there's a mid-latitude cyclone close to South Africa, close to the Western Cape, and it's winter. You have low temperatures, that's also a giveaway, hopefully, that it's winter. You have clear skies, so you might remember reading the synoptic weather stations or the station models. You maybe remember that the little circles over there means that there is no clouds. So if you see no clouds inland, it means it's winter. And then finally, you look for that high pressure cell over here. You look for the Kalahari high, big H right there. That means that the air is sinking. Reason why it's sinking is because it's cold. Oh, and if you're really not sure, maybe just check what date the map was published. You'll see the date on the right-hand side over there. So, summer is when the interior parts of South Africa get their rain. What happens is that, yeah, this will work. This area, this part of the land gets hot, and as it gets hot, the air starts to rise. Sometimes you will see it even as a low pressure system on a synoptic weather map. Let me see. Here we have the one high pressure is. I'm not quite sure if this is supposed to be connected to this. I think it is. I think this whole thing is the high pressure system. So this is the uh, South Atlantic anticyclone. Here is the South Indian anticyclone. You can see how far south they are now compared to when we were looking at uh, over here, there. There you can see it's right next to South Africa. And here you can see it's all the way down the bottom of the map. Okay, so they move down and they move south and they move outwards away from the coastline. In winter, they move north and towards the coastline. Here we have our low pressure system. Go. That tells me that this is summer. I can also see how far south this mid-latitude cyclone is. I can't even see the whole cyclone. I just see the cold front. So it's very far south. I can see, zoom in, go the little station models on the synoptic weather map. They tell me that this is mostly cloudy or completely cloudy. So there is rain that is coming. Okay, there you can very clearly see the low pressure cell. So it is an anticyclone or a low pressure system. Oh, I'm here. Okay, so we have a low pressure that forms at the surface. Then it means that the inversion layer, that layer that was blocking the moisture from coming in, also rises up. It also gets lifted. And as it gets lifted, there's finally a gap for that moist air. Yeah, this gets lifted. And when that gets lifted upwards, this air can blow up and inland. So finally, we get moisture from the ocean. The inversion layer is still there. We just don't notice it because it's further up in the atmosphere. Same thing with the Kalahari anticyclone. The anticyclone is still there. It hasn't just disappeared. It's just further up in the atmosphere, so we don't record it on the maps. Okay, everything moves southwards. We mentioned that the anticyclones move southwards. And then we finally get to the air from the ocean currents. So I'm going to explain how the thunderstorms work, but basically where we have the cold ocean currents, and where you have the cold ocean currents over here, there's not much humidity, so you won't get much rainfall. Where you have the warm ocean currents, there is a lot of humidity, so a lot of rain. And now this can also bring moisture in, especially since we have a high pressure, right, where is it? Find it. Yeah, there. We have a high pressure system right here. And if you remember, wind blows away from the high pressure and towards the low. So the wind will be blowing from there to there, from the ocean to the interior, to the land. And that blowing wind brings that moisture with because it blows over the warm ocean current. So it picks up all of that evaporated water and blows it inland. Now the same thing happens on this side over here. The same thing happens with this high pressure system. So it picks up the air from here, blows it inland, and they collide. They collide halfway through. And that brings us to moisture fronts. So I mentioned that the wind carrying that warm, moist air is blowing in, and the wind that is fairly dry, fairly cold, also blows in from the other direction, and they collide. Where you have two areas of different moisture air, you have a moisture front. So it's a place where you have warm, moist air meeting cold, dry air. In this case, it's moist air from the Indian Ocean and dry air from the south or western part of the ocean. So I don't know if this is going to work, but I want to try it. So the last time I tried doing sketches, again, it's being difficult. It looks like it could work. Let's try. So right here, we're doing this as summer. There we go. I'm going to add a high pressure system here. Okay, that's not too bad. So far, so good. Okay. So far, that's not awful. So this is the high pressure, the low, high. Another term for these large, high, and low pressure cells are troughs and ridges. A trough is an area of low pressure between two highs. Where it's high, that is the ridge. Okay. So where it's high, like at the top of a hill, it is a ridge. Where it's low, it is a trough. So large high pressure cells like this one that we had over here, this large oblong high pressure cell, that would be a ridge. This one over here, that one as well. And then this low pressure cell in between them would be the trough. High, ridge, low, trough. I'm changing color to red because it's supposed to be warm. Hello, welcome back. And the wind is blowing away from the high pressure. Oh, it'll do. Blowing over the warm ocean current. Let's maybe make this over here pink. And it blows inland, spiraling inland towards. Then over here, by this one, let's first highlight this cold blue. Go. We have the air blown away from the high pressure. and move land towards the low. Okay, so hopefully you're seeing that this air will collide. Let's make the colliding air purple. So where this air collides, you have a moisture front. So you have moist air over here from the warm ocean currents. You have dry air over here from the cold ocean currents. Where they're meeting, you have a moisture front. And what happens is that the warm air, when it meets the cold air, because the warm air is lighter and less dense, it will rise up over the dense cold air. And as it rises, it will condense. And because it rises so quickly, it condenses very quickly and it forms clouds. Stickers? Yay, clouds! Perfect. Ah, my diagram looks amazing now because I have clouds. And maybe you'll remember that they are cumulonimbus clouds, where you have air rising very quickly, they will form very tall clouds, and those are cumulonimbus clouds. There we go. So here we have our line of thunderstorms. That's literally what they're called, line of thunderstorms. So this line of thunderstorms can actually be, well, one, very good. It's very beneficial in terms of that's where we get our water from. It's our main source of water inland. But the thunderstorms themselves can be very destructive. It's a accumulation of thunderstorms. It's not just one storm. So they bring with more damage, more rain, more destructive winds. So thunderstorms can easily be examined in a way, how are they beneficial? And then you can think of rainfall and economy and agriculture and all of those things. And you can also say, what are the consequences or what are the negative impacts of these line thunderstorms? And then you can say destruction from the storm, destructive winds, maybe floods from excessive rain. So there's a lot that can be looked at there. This is how you might usually see them on a map, on a diagram. So here we have our high pressure, perfect. It is spiraling inland. Here we have another high pressure. It is cold and dry, spiraling inland. And where they meet, we have the moisture front. The cloud will form on the humid side. So let's move them up a bit. So the clouds will form on the humid side. It will form where the moisture is coming from, just like you'll see over there. I don't think, oh, that's also another nice diagram. South Indian high pressure cell, wind blowing in. There's the moisture front. South Atlantic high pressure cell blowing in dry, cold air. The side will stay fairly dry. And here you can see, open this a bit more, read what's on it. So this would have been a warning because of one of these storms. So you can see there was a yellow warning, yellow level 4 warning. There was rain. There could be, do they mention any potential damage? Strong possible damage, large hail, heavy downpours likely. Okay, so there's definitely damage that can happen from a storm like this. But at the same time, it's also our source of water. So let me just check if I'm missing anything. We've covered moisture fronts. We've covered troughs and ridge. So a trough is where it dips down. Ridge is high. So a trough is a low pressure between high pressure cells. Ridge is a large high pressure cell. Um, Warm air rises, forms clouds. Hopefully, we know that. Line storms, or line thunderstorms, because they're literally a line of storms. And we typically see them on very hot days, cause a lot of damage. And oh, why do you only see these storms in summer? Because in winter, you have the Kalahari anticyclone that's close to the ground. And because of that, go, and the temperature inversion, you don't have wind blowing inland. So you won't have a high pressure cell blowing air towards another high pressure cell. They always blow away from the high. So you have to have a low pressure cell, which means it has to be summer. Also, the inversion layer blocks any of that moisture coming in. So you have two things that you need for the storm. One, you need a low pressure cell inland. Two, you need moist air to actually blow inland. I'm hoping that makes sense. Oh well, that's okay. Well, I'm hoping that this makes sense. I'm hoping that it helps anyone that has been struggling with this section. And maybe you learned something, maybe this answered a few questions, and you're welcome to let me know if there's anything specific that you're struggling with. Okay, well then, I hope you have a lovely day, and I will see you again next week. Thank you for joining. Cheers.